Your next trillion parameter model won't fail because of a gradient explosion or a lack of training data. It will fail because the local power grid physically cannot deliver the 50 megawatts required to keep your cluster alive. For the past decade, we've lived under the scaling law era where more compute and more data reliably yielded better intelligence. But by 2026, we are hitting an inflection point where the divergence between model demand and facility capacity becomes a chasm. While software efficiency like flash attention 3 or quantization techniques can offer linear gains, the exponential demand of models like GPT-5 or Llama 4 is colliding with the rigid, slow-moving reality of utility infrastructure and power substation lead times. We are moving from a compute-bound world to a facility-bound world where intelligence is directly limited by electricity. By the end of this lecture, you will understand why the current AI roadmap is fundamentally unsustainable without a radical shift in physical engineering. But wait, can't we just optimize our way out of this with better algorithms? In the world of senior software engineering, we often treat hardware as an infinite abstraction layer. We talk about flops and QDA kernels as if they exist in a vacuum. However, in the 2026 landscape, the model-only fallacy, the belief that algorithmic breakthroughs can bypass physical limits, is crumbling. You can write the most efficient Triton kernel in the world, but if the GPU hits its thermal throttle limit due to insufficient liquid cooling at the rack level, your software optimization provides zero real-world throughput gain. We are seeing a shift where low-level systems engineering must now account for ambient temperature, humidity, and voltage sag. When you are deploying Blackwell-class GPUs, drawing 1 and 200 W each, the bottleneck isn't your Python code. It's the physical copper traces on the PCB and the heat pipes carrying away the thermal energy. Is this approach of just throwing more hardware always the right move? I'll show you a counterexample immediately. The industry consensus among top-tier infrastructure architects has shifted. We are no longer compute-bound, we are facility-bound. Leading researchers are warning that the next generation of AI clusters will require direct liquid cooling, DLC, as a baseline, not an exotic option. As we scale toward 100,000 GPU clusters, the complexity of managing 100 megawatts of power and the associated cooling load becomes the primary engineering challenge, overshadowing the model architecture itself. We are seeing a reality check where the cost of tokens is being driven more by the price of industrial chillers and power transformers than by the silicon itself. If you are an architect planning for 2026, you must stop looking at just the TOPS per watt and start looking at the total cost of ownership of the cooling loop. This is the theory. Real-world data shows something much scarier regarding how we actually build these systems. So, how does a modern engineering roadmap change under these conditions? We move to physics-first engineering. This means instead of starting with the model size and working down to the hardware, we start with the available power and cooling envelope and work up to the model architecture. In 2026, when you evaluate an AI vendor or an internal project, you will judge its viability based on PUE, power usage effectiveness, and WE, water usage effectiveness, targets. If a project requires a cluster density that the regional grid can't support without a 5-year substation upgrade, that project is effectively dead on arrival, regardless of its theoretical performance. This paradigm shift forces us to integrate energy sourcing and cooling plant design into the very first step of the development cycle. Up until now, we've looked at the surface. Let's look at the actual stack that's breaking. The new AI infrastructure stack is no longer just layers of software. It is a vertically integrated unit where the power grid is the foundation, and the silicon is merely the tip of the spear. We must view the energy grid, the cooling infrastructure, and the silicon as one integrated unit. At the bottom, we have high-voltage substations. Above that, the facility-level liquid cooling loops, then the rack-level power distribution units, PDUs. And only then do we reach the GPU and HBM. In 2026, a failure at the cooling layer is just as catastrophic as a bug in the model's weights. This holistic view is what separates amateur AI hype from professional-grade infrastructure. Silicon itself is reaching a wall that no amount of cooling can fix. In the next chapter, we'll dive into why GPUs and HBM are the first to crack under this pressure and the specific bottlenecks in the silicon itself. In the current AI landscape, capital is no longer the primary accelerator. Lithography and fab capacity are. When you order a cluster of H100s or B200s, you aren't just buying hardware, you are entering a multi-year geopolitical and logistical queue. The backlog at major foundries like TSMC means that even if a startup raises $1 billion today, they might not see their compute resources for 52 weeks. This lead time trap creates a massive disconnect between software innovation and hardware reality. By the time your infrastructure arrives, the model architecture you optimize for might already be obsolete. We are seeing a shift where the physical scarcity of 4nm and 3nm nodes dictates the roadmap of global AI development more than algorithmic breakthroughs ever could. But why can't we just build more factories to meet this demand? The answer lies in a specific, highly complex packaging step that most people overlook. The true gatekeeper of AI hardware isn't just the silicon die itself, but a process called CoWoS chip-on-wafer-on-substrate. This advanced packaging technique allows high-bandwidth memory to be placed extremely close to the GPU core to minimize latency. Currently, the global capacity for CoWoS is the narrowest part of the funnel. Even if we increase wafer production, if we cannot package them, the chips stay on the shelf. In 2026, we are seeing enterprises realize that compute is not a liquid commodity. You cannot simply scale horizontally when the vertical supply chain for interposer layers is physically capped. This realization is forcing architects to rethink their reliance on general-purpose GPUs. If the mainstream supply is physically restricted, is it time to look at specialized alternatives designed for specific tasks? This brings us to a critical comparison. To bypass the GPU supply wall, the industry is pivoting toward ASICs, application-specific integrated circuits. While NVIDIA's GPUs offer unmatched flexibility for diverse research, custom silicon like AWS Trainium Google TPUs or Meta's MTIA are being optimized for one thing: the transformer architecture. These chips strip away the overhead of general-purpose graphics processing to focus purely on tensor operations and high-speed interconnects. For a senior engineer, the decision to migrate from GPU to ASIC involves a trade-off between software maturity and cost efficiency. GPUs have the CUDA ecosystem, but ASICs offer a way to escape the NVIDIA tax and lead time delays. However, switching to custom silicon requires a massive investment in compiler stacks and kernel optimization. Is the flexibility of a GPU worth the wait, or is specialized silicon the only way to scale in 2026? But wait, even with the fastest chip, your AI model will hit another wall if the data can't reach the core fast enough. We often talk about TFLOPs, but in the world of large language models, compute power is often idle. The real bottleneck is the memory wall. LLM inference is memory-bound, meaning the speed at which we can move model weights from memory to the processor defines the tokens per second performance. This is why HBM3 high-bandwidth memory has become the most precious resource in the data center. Unlike standard DDR5, HBM uses vertical stacking and a wide interface to provide terabytes of bandwidth. Without HBM, your 2000 TFLOP GPU would be like a Ferrari stuck in a school zone. As models grow to trillions of parameters, the pressure on memory bandwidth scales exponentially. If you are designing a real-time AI service, you need to understand that the HBM wall is what will determine your latency floor. But is it enough to just keep adding more HBM stacks? Let's look at the data. Let's analyze the raw numbers. In the last decade, compute throughput has increased by nearly 1,000x, while memory bandwidth has only increased by about 30x. This massive discrepancy is why modern AI chips are essentially memory with a little bit of logic attached. When we compare high-end chips, the primary differentiator for inference performance isn't the core count, but the GBS of the memory bus. For instance, moving from HBM3 to HBM3 isn't just an incremental update. It's a desperate attempt to keep the processor fed. If your project involves long context windows or massive batch sizes, your infrastructure cost will be driven almost entirely by HBM pricing and availability. This table shows the brutal reality. We are gaining more brains, but the veins to carry information are not keeping up. This leads to a surprising realization about the cost of moving data versus calculating it. In silicio, distance is death. The energy required to move a bit of data across a chip can be 1,000 times higher than the energy required to perform a mathematical operation on that bit. This is why data locality is the most important concept in modern AI systems design. If the data is far from the processing unit, you aren't just losing time, you are burning electricity and generating heat. This is why we see designs moving toward processing in memory, PM, and tighter 3D stacking. For developers, this means that optimizing for catchy hits and minimizing data movement is more impactful than squeezing out a few more TFLOPs. We have reached the physical limit of how fast we can push electrons across a silicon substrate without melting it. Now that we understand the silicon wall, we must face the even more terrifying barrier, the power grid itself. Next, we look at how kilowatts are becoming the ultimate constraint. In the traditional data center landscape, a standard server rack consumed between 5 to 10 kilowatts. This was the benchmark for years, driven by general-purpose CPU workloads and standard virtualization. However, with the advent of AI clusters, we have witnessed a vertical jump in power requirements. An NVIDIA HGX 100 system alone can pull over 10 kilowatts in a single 4U or 6U chassis. When you scale this into a full cluster, we are looking at 100 kilowatts to 120 kilowatts per rack in 2024 and 2025. This isn't just a minor increment, it is a fundamental shift in how we architect the facility floor. The power density has increased tenfold, while the physical footprint of the rack remains largely the same. This creates an localized energy intensity that challenges every component of the electrical distribution chain, from the transformers to the busbars. If your infrastructure was built for the 2010s, it is physically incapable of supporting even a single modern AI rack at full load. But the power draw is only half the story. The physical delivery of that power creates its own set of engineering nightmares. Have you ever wondered if the actual copper cables can even fit behind the server anymore? This physical bottleneck is exactly what we will examine next. When you push 100 kilowatts into a single rack, the physical infrastructure starts to resemble an industrial power plant rather than an IT room. The copper required to carry this current is incredibly heavy and thick. Engineers are now struggling to manage the physical volume of power cables within the restricted space of a standard 19-inch or 21-inch rack. We are seeing a move toward busbar architectures where solid metal bars replace flexible cables to handle the massive amperage. Furthermore, the weight of these racks is skyrocketing. A fully populated AI rack with GPUs, high-speed networking, and liquid cooling manifolds can weigh over 1.5 tons. This exceeds the floor loading capacity of many older Tier 3 data centers. We are reaching a point where the floor might literally buckle under the weight of the intelligence we are trying to compute. It's a literal heavy problem that software engineers rarely consider when they spin up an instance. But even if the floor holds, how do you manage the sheer volume of heat generated in such a tight space? This is where the standard cooling designs of the last 2 decades completely fall apart. The question is, can we continue to iterate on current designs, or do we need a total teardown? Most existing Tier 3 data centers were designed for a world where heat was managed by moving large volumes of cold air. In that world, hot aisles and cold aisles were enough to keep CPUs within safe operating temperatures. But in the AI era, those facilities are becoming effectively obsolete for high-end training. A standard Tier 3 facility often lacks the power delivery per square foot and the cooling redundancy required for sustained 100% GPU utilization. If you try to run an H100 cluster in a facility designed for 10 kW racks, you will experience a thermal throttling almost immediately. The GPU will downclock its frequency to protect itself from melting, which means you are paying for premium compute, but only getting a fraction of the performance. This infrastructure stress is forcing companies to either build custom AI factories or seek out specialized providers that can offer 100 kW plus per rack support. This is no longer just an IT upgrade, it's a massive civil engineering challenge. The cost of retrofitting an old data center is often higher than building a new one from scratch. But wait, what does this actually do to your monthly bill? Let's look at the cold, hard numbers of OpEx in this high-density world. When we calculate the operational expenditure or OpEx for these AI clusters, the numbers are staggering. We aren't just paying for the electricity the GPUs consume, we are paying a massive premium for the infrastructure to support that consumption. In a high-density environment, the cost of cooling can account for nearly 40% of the total energy bill if the facility is inefficient. As we move towards 700W and 1000W GPUs, the cost to keep them cool scales non-linearly. For every dollar spent on raw compute power, you must budget significantly for the power distribution losses and the cooling systems overhead. Furthermore, the specialized maintenance for high-density, liquid systems adds a layer of labor cost that traditional data centers never had to deal with. If you are planning a multi-year AI project, ignoring the escalation of power and cooling costs will lead to a budget cliff where your infra costs exceed your model's revenue potential. We have to move beyond air cooling, but that transition comes with its own set of engineering risks. Do you know why air cooling literally hits a physical wall at 20 kW? The answer lies in the physics of fluid dynamics, and it's why your next server might be underwater. Air is a terrible conductor of heat compared to liquids. To cool a 700W GPU using only air, you need to move an immense volume of it across the heatsink. As rack density approaches 30 kW and beyond, the fans required to move enough air become so loud and consume so much power that they become counterproductive. We hit what is known as the sonic wall and the power wall for fans. In a 100 kW rack, the fans alone would consume a significant portion of the rack's power budget and create noise levels that are dangerous for human operators. Liquid, specifically water or specialized dielectric fluids, has a heat carrying capacity that is orders of magnitude higher than air. This is why we are seeing a forced migration toward liquid cooling. If you are building for 2026, air cooling is no longer an option, it is a legacy constraint that will throttle your performance. The physics are simple. Water can transport heat 300-500 times more effectively than air. But bringing water into a room full of million-dollar electronics, that's where the fear and the complexity begin. Let's look at the 2 primary ways the industry is trying to solve this without short-circuiting the entire cluster. There are 2 dominant technologies emerging: direct-to-chip, DLC, and immersion cooling. DLC uses cold plates that sit directly on the GPUs and CPUs, with liquid circulating through tubes to carry heat away to a heat exchanger. It's the most common approach for NVIDIA's Blackwell systems. Then there's immersion cooling, where the entire server is literally dunked into a tank of non-conductive dielectric fluid. While immersion is incredibly efficient, it is a maintenance nightmare. Imagine having to use a crane to pull a server out of a vat of oil just to swap a failed DMM or a network card. This complexity is why many enterprises are hesitant. You need specialized plumbers, not just IT technicians. The risk of leaks is a constant anxiety for data center managers. If a liquid loop fails in a 100 kW rack, the downtime isn't just one server, it could be the entire row. This shift transforms the data center from an electronics warehouse into a complex fluid management facility. But there is another environmental cost that often gets ignored in the hype of liquid cooling efficiency. The sheer volume of water we are consuming. Is our AI dream drying up the local reservoirs? Data centers are becoming massive water consumers. To cool megawatts of heat, many facilities use evaporative cooling, which literally boils off water to chill the systems. A large AI data center can consume millions of gallons of water per day. In regions facing water scarcity, this has become a major political and environmental flashpoint. Even if you use closed-loop systems, you still need a primary cooling source that often relies on municipal water. As we scale to GPT-5 and beyond, the water footprint of a single training run is becoming a metric as important as the carbon footprint. We are seeing a move toward waterless cooling designs, but they are more expensive and less efficient in hot climates. This creates a geographical constraint. You can't just put an AI data center anywhere. You need power, yes, but you also need a massive, reliable water source and the social license to use it. If the local community is facing a drought, your data center's cooling needs will be the first thing scrutinized. This brings us to the ultimate metric of data center efficiency, PUE, and how it's being redefined in the era of liquid-cooled AI. It's not just about the ratio anymore, it's about the total resource impact. Power usage effectiveness, or PUE, has long been the gold standard for measuring data center efficiency. In the air-cooled era, a PUE of 1.5 was common, and 1.2 was considered elite. With liquid cooling, we can achieve PUEs as low as 1.5 because we eliminate the massive energy draw of fans. But here is the trap: a low PUE doesn't mean a low power bill. If your total power draw has gone from 10 megawatts to 100 megawatts, a PUE of 1.5 still results in a massive absolute energy cost. We also have to consider water usage effectiveness, WUE, and carbon usage effectiveness, CUE. The thermal ceiling is a complex web of electricity, water, and physical space. If any one of these hits a limit, your AI scaling stops. We've seen how heat and power density are forcing a total redesign of the rack. But even if you solve the cooling and the density within the building, you face the final boss of physical limits, the power grid itself. You can build the most efficient liquid-cooled data center in the world, but if the local utility can't give you 100 megawatts, it's just an empty shell. In the next chapter, we look at the looming grid crisis and why geography is once again becoming destiny for the tech industry. The scaling laws for AI models are hitting a concrete wall, and it's not made of silicon, it's made of copper and transformers. In major tech hubs like Northern Virginia or Dublin, the wait time for a 500-megawatt grid connection has ballooned to nearly a decade. When a hyperscaler requests power today, the utility provider often responds with a 2030 or 2032 completion date. This isn't just a logistics delay, it's a structural failure of our legacy electrical infrastructure to adapt to the exponential density of A200 and B200 clusters. While we fight over GPU allocations, the real scarcity is the high-voltage substation that hasn't been built yet. This gridlock forces a brutal choice: wait for years or move to the middle of nowhere where power is plenty but latency is high. This mismatch between software speed and infrastructure reality is the grid gap. But wait, is the shift to green energy actually helping or making this harder? There is a fundamental physics mismatch between how AI consumes power and how renewables generate it. AI workloads, especially training, require 24/7 baseload stability with nearly 100% uptime. However, wind and solar are inherently intermittent. The sun sets and the wind stops. In industry reports, we see that a data center running on 100% to renewables without massive battery storage or nuclear backup would experience frequent brownouts that crash training clusters. Currently, the energy density of batteries isn't sufficient to bridge these gaps for a 500 MW facility for more than a few hours. This means that despite net zero marketing, most AI centers still rely heavily on natural gas or coal as a stabilizing floor. If we want truly green AI, the storage technology must evolve as fast as the LLMs. But how are the biggest players taking matters into their own hands right now? To bypass the grid crisis, we are seeing a shift toward behind-the-meter or on-site power generation. Large tech companies are no longer just customers of utilities. They are becoming utility providers themselves. This involves installing industrial-grade gas turbines directly on the data center campus to provide immediate power while waiting years for a grid connection. More ambitiously, the industry is pivoting toward small modular reactors, or SMRs. These are compact nuclear plants that can be built in factories and deployed on-site to provide clean, high-density baseload power. While SMRs are still in the licensing and prototype phase, the massive capital being poured into them by AI giants suggests they are the long-term bet for 2030. This transition from consumer to producer is a massive shift in the data center operator's business model. Does this solve everything? Not quite, because even if you have the power, you might not have the permission to use it. Grid congestion is creating a new economic reality: the stranded GPU problem. If you have 10,000 Blackwell GPUs ready, but the grid only gives you enough power for 5,000, half of your multi-million-dollar investment is literally sitting in the dark. This leads to power curtailment, where training clusters are forced to throttle their performance during peak grid demand hours to avoid crashing the local city power supply. The economic impact is devastating, as it extends training timelines and inflates the cost per token. In some regions, data centers are being asked to shut down entirely during heat waves to protect residential cooling. This volatility is forcing AI companies to look beyond traditional tech hubs to places with energy surpluses. But this move raises a whole new set of questions: where exactly will the world's intelligence factories be located in the next 3 years? Let's look at the new map of AI geopolitics. The geography of AI is bifurcating into core and edge locations based on power costs versus data proximity. Training clusters are increasingly moving to remote regions like Iceland, Norway, or even the deserts of the Middle East, where energy is cheap, abundant, and easily cooled by the environment. For training a foundation model, the 100ms latency to the user doesn't matter, the cost per kilowatt hour does. Conversely, inference hubs must stay close to major cities the edge to ensure low latency response for end users, despite the high power costs in those areas. This creates a strategic divide. You train where it's cheap and infer where the people are. Engineers now have to manage distributed architectures that span continents. Is this decentralization a choice or a necessity? It's becoming both as local governments start to view power as a national security asset. But what does the new global power map look like? We are witnessing the emergence of sovereign AI hubs, nations that leverage their energy surplus to become the cloud providers of the future. Countries like the UAE, Saudi Arabia, and Canada are positioning themselves as global AI workshops by offering subsidized energy and streamlined permitting for gigawatt-scale campuses. In this new world order, energy exports are being replaced by intelligence exports. Instead of shipping oil or gas, these nations are turning that energy into compute tokens and selling them back to the world. This shifts the power away from traditional tech capitals like Silicon Valley toward energy-rich jurisdictions. If your startup's training budget is 70% to electricity, you will go where the power is guaranteed. But moving to these new hubs isn't as simple as shipping a few servers. There are massive regulatory hurdles to clear first. As AI data centers expand, they are hitting environmental walls. It's not just about electricity, it's about water and noise. A large AI facility can consume millions of gallons of water per day for cooling, leading to local protests and strict new regulations in places like Arizona or the Netherlands. Some cities have even placed moratoriums on new data centers because they compete with residential areas for both water and grid stability. Developers are being asked, how does your 1 gigawatt center benefit the local community? If the answer is only more tax revenue, it's often not enough anymore. This regulatory friction is adding 2-3 years to every project. Many ask if we can just move everything to space or underwater, but the reality is much more grounded. How should your technical strategy account for these environmental barriers? Let's answer some of the most pressing questions about these expansion limits. In the AI era, the role of the CTO has fundamentally changed. You are no longer just an architect of software, you are an architect of energy. Every architectural decision from model size to the choice of precision, FP8 to BAS and T8, is now an energy decision. We've seen that the cost of power is now the single largest line item in the training budget, surpassing the cost of the GPUs themselves over a 3-year life cycle. Therefore, your 2026 strategy cannot just be more GPUs. It must be better energy efficiency and diverse location sourcing. If you ignore the grid, your AI dreams will literally run out of juice. Energy strategy is now the primary competitive advantage in the race for AGI. But how do you actually implement this as an engineer or leader? In the final chapter, we will build your infrastructure playbook for 2026 to navigate these physical limits and win. By 2026, the myth that more GPUs equals linear performance scaling will be thoroughly debunked by the reality of physical bottlenecks. As a senior developer or infrastructure architect, your first task is navigating the brutal trade-offs between centralized megawatt-scale data centers and distributed edge clusters. While centralized hubs offer the lowest latency for internode communication via InfiniBand or NVLink, they are increasingly hitting power walls where local grids simply cannot provide the additional 20 to 50 megawatts required for the next expansion. Conversely, distributed clusters bypass local grid constraints, but introduce a latency tax that can cripple synchronous training workloads. You must evaluate your cluster design based on 3 pillars: the cost of specialized cooling, the latency tolerance of your specific model architecture, and the raw physical scalability of the site's power infrastructure. Choosing the wrong quadrant in this matrix doesn't just increase costs. It can lead to a project-killing ceiling where you have the budget for more H200 or B200 units, but nowhere to plug them in. But before you sign a multi-million-dollar colocation contract, how do you actually audit the site's physical readiness? Vetting a data center provider in 2026 requires looking far beyond the sales brochure's uptime guarantees. You need a resiliency checklist that focuses on the physical survivability of high-density compute. First, verify the liquid cooling readiness. If a provider isn't already supporting rear-door heat exchangers or direct-to-chip liquid cooling, they won't handle the 700W to 1000W TDP of next-gen GPUs. Scrutinize the power usage effectiveness, or PUE. In a world of rising energy costs, a PUE above 0.3 is a financial liability. You also need to confirm grid diversity. Does the facility have feeds from 2 independent substations, or are they vulnerable to a single point of failure in an overstrained local grid? Experience shows that many AI-ready facilities are actually legacy DCs with fancy marketing, struggling to manage the harmonic distortion and massive power swings common in LLM training runs. If the provider cannot show you a clear path to 100 kW per rack, your scalability is an illusion. But even with perfect hardware, can software strategies mitigate these physical walls? Future-proofing your AI strategy means shifting hardware maximalism to hardware-agnostic software architectures. Since we know physical limits power, heat, and the memory wall are inevitable, your software stack must be designed to circumvent them. This involves aggressive use of sparse weights and quantization techniques, such as 4-bit or even 2-bit precision, to reduce the HBM pressure. Furthermore, adopting asynchronous training and model distillation allows you to leverage heterogeneous clusters, mixing high-end B200s with older A100s, or even specialized ASICs without the entire pipeline waiting for the slowest node. Smart orchestration at the software layer can shift workloads based on real-time energy, pricing, or thermal loads across different data center zones. We call this infrastructure-aware development. By treating the physical layer as a set of dynamic constraints rather than static resources, you can maintain a competitive edge even when the grid reaches its limit. This brings us to our final conclusion. The physics of AGI. Is our path to superintelligence actually a race against thermodynamics? Let's look at the final verdict. As we conclude this deep dive into AI data center limits, one truth remains: intelligence is fundamentally constrained by thermodynamics. In the industry, we often get distracted by the latest model release or a new API, but the long-term winners of 2026 and beyond will be the physics-first thinkers. These are the leaders who understand that scaling AGI isn't just about writing smarter code, but about managing the massive entropy and energy flux required to sustain it. If you ignore the power grid, the cooling limits, or the HBM bottlenecks, your AI dreams will eventually break against the hard wall of physical reality. Efficiency is no longer an optional optimization. It is the primary survival mechanism for any AI-driven enterprise. You must transition from a mindset of unlimited growth to one of optimized scaling. This shift in perspective separates the engineers who build sustainable systems from those who merely burn through VC capital without a path to physical feasibility. But how do you decide when to push the limits and when to pivot? It comes down to a specific decision logic. To survive the 2026 infrastructure crisis, you need a repeatable logic for decision-making. Every time you face a scaling requirement, follow this process. First, assess the workload. Is it training heavy or inference heavy? Then, audit your physical constraints. Don't look at your cloud dashboard. Look at the actual thermal and power limits of your provider's region. Next, perform a brutal cost-benefit analysis. If adding 10% to more power capacity increases your OPEX by 40% due to specialized cooling requirements, you have reached a point of diminishing returns. In such cases, the logic dictates a pivot to optimization, first refactoring the model, using smaller parameter counts with better data, or moving to the edge. Only when the physical headroom is clear and the cost-to-performance ratio is healthy should you commit to physical expansion. This structured approach prevents the infrastructure debt that many companies are currently accumulating. Now that we have mastered the physical layer, how does this connect to the software that actually runs the AI? We have spent this entire lecture series dissecting the physical limits of AI from the silicon die to the global energy grid. You now have the infrastructure playbook to navigate 2026. But the story doesn't end here. The physical layer is merely the foundation. To truly harness this power, we must look at how software is evolving to abstract these complexities away. This leads us to the concept of the software-defined AI gateway, a layer that dynamically manages these physical constraints so that your application developers don't have to. In our next series, we will bridge the gap between this dirt and wires analysis and the world of agentic workflows and automated AI orchestration. We will explore how the software stack is being rewritten to handle the very physical bottlenecks we discussed today. Thank you for joining this masterclass on the physical limits of AI. Stay tuned as we move from the physical foundation to the software-defined future of AGI. See you in the next series.